Let's start. So, everybody, new day, new stuff in pre-calculus. Okay? And so we're going to start with a completely new topic right now. Okay? Still kind of works in with a little bit of trigonometry. Okay? We'll see how the trigonometry fits into it as we move through it. Okay? But we're going to start off with, Clark, as you said, vectors. Okay. All right. So, a vector, okay? A vector is another way of kind of putting points on a coordinate plane, okay? So, kind of the, basically what a vector is, it's a direction and a magnitude together. And I'm going to say length, and then just call it magnitude. Okay? So, we're going to do an example of a classical point, a regular point.
So this is the first topic for the next test?
Yeah. Okay. And then over here, I have the vector version. Okay. So, with a regular point, okay, how we define it is basically, let's say this is the point right here, 3, 2, okay? We define it by going over 3 spaces in the x direction and then 2 spaces in the y direction. And that's how we get to that point there, okay? With a vector instead, okay, you're going to define it as basically a line segment or array pointing to that point there, okay? And how the information here is encoded is, instead it's going to be an angle here, okay, and then a length, okay, so a magnitude. So in this case here, it would be whatever the tangent of
square root of
2/3
13.
is. Or tangent. Hang on one second. No, that would be. Okay, so this would be like 33 degrees here. And then the magnitude here would be the square root of 13. That's how long it would be. Okay, and so that point there, okay, we could define that as a vector as basically being, root 13, basically angle 33. Okay. And that's one way we can do things, all right? But that's what a vector is. So it's a direction and a length, okay? Sometimes referred to as a directed line segment, okay? Now, there are many different ways to write vectors, okay? We're going to start off by looking at vectors in component form. Okay. So vectors in component form. And so what that's going to be is basically, okay, we can define the vector in component form as basically vector v equals v1 comma v2, where v1 is the horizontal component, and v2 is a vertical component, okay? So, when it's written this way, it's going to look very much like, a set of coordinates, okay? And in a way, they would kind of behave under the same kind of rules. The big difference, though, is with a normal set of coordinates, okay? So when I'm looking at, like, I just told you to point, like, 3, 2, okay, earlier, I'm basing that off the origin of the graph, okay? A vector does not have to be based off the origin. A vector could be anywhere on a graph, okay? And in fact, we typically define a vector as being between 2 points, okay? So we would say V is the vector between P and points should say between points P and Q.
Is that something special? Why P and Q?
Oh, P for point, and then Q because Q comes after P.
Oh. That makes sense, yeah.
Between
Sure.
points P and Q, okay? And in fact, how we would typically define this is if P is the point P1, P2, and Q is the point Q1, Q2, then vector V can be written as P1 minus Q1, comma, P2 minus Q2, okay? So I can write up here is that V1 is the difference between the x's in the first point, and V2 is the difference in the y's between the 2 points, okay? And so that's how you make a vector in component form, okay? Any questions about that? And we'll draw a picture of what we mean by this in a second, okay? All right. This right here, these components will tell us the direction of the vector, okay? But they don't tell us how long the vector is, okay? For that, we would need a different measurement. We would need the vector's magnitude, okay? And that's easy enough to find, okay? Okay. The magnitude, which is what the length is, okay, of a vector, is basically going to be, in this case, it's written as what looks like a double absolute value of V, just stands for magnitude. It's just the notation for vectors, okay? And it's going to be equal to the square root of the difference between P and Q squared plus so the horizontal part squared plus the vertical part squared, basically. Okay, so that's the magnitude, okay? It's basically applying the Pythagorean theorem, okay, if you will. Okay, if you think of these things, and we'll draw it out again. We're going to look at an example of a vector here in a second, and you'll see how we get all these, okay? But these are sort of all the parts here, okay? Some basic terminology, okay? If the magnitude of V is 1 or equals 1, V is a unit vector.
In the unit circle.
Just like in the unit circle, yeah.
Uh-huh.
Okay? In fact, you could think of the radius of the unit circle as actually being a unit vector.
Wow.
Okay.
Yeah.
And it's another way you can tie vectors and the trigonometry together. Okay? They do go hand in hand.
Yeah.
Okay? Ultimately, okay? All right. Any questions about that so far? Just a bit of terminology. Okay. Let's take a look at what we mean by all this with an actual picture. Okay? So, let's go ahead and draw a graph up here. So, we'll say, draw up 2 points here. All right. This point here would be, let's make it 1, 2. And this point up here, let's make it 4, 4. Okay? So, a vector between these 2 points, okay? There's actually 2 vectors between these 2 points. The first one is a vector from going from 1, 2 to 4, 4. So it's a vector in that direction there, okay? And so the vector, this vector here, we call it V, would be 4 minus 1, comma, 4 minus 2. Or the vector 3, 2. Okay? Its magnitude would be root 13. So this 3 squared would be 9, 2 squared is 4, 4 and 9 is 13, and we take the square root, okay? So that's one way we could do it, okay? The other vector we have here is the vector going from 4, 4 to 1, 2, okay? And we can actually call that vector negative v because it's, if you notice, it's going to be just the negation of these up here. It's going to be 1 minus 4, comma, 2 minus 4, okay? Which would be equal to minus 3 minus 2. What would the magnitude still be, though? It would be what?
13.
Root 13, okay? So even though the signs flipped, the magnitude is still a positive value. Why would that be the case? Magnitude is what?
Square. Length.
Right.
It's a length, right? Can length ever be negative? Does that make any sense?
No,
No.
it would though.
Okay. Negative length doesn't make any sense,
Can
okay?
you put these notes in the things? I can't get the graph up on my stuff.
Put the notes in the
Can you put like the notes
Online.
on
modules.
Yeah, on modules.
canvas, yeah.
Okay.
Yeah, I'll do that. I usually do that. Okay. It should be there. It'll be under modules, okay, for this chapter. It'll be, looks like chapter 6, this will be the first thing in there.
Because I tried to see if you had yesterday's notes up and I didn't see those.
Well, because there was no class yesterday.
You canceled class.
Well, no, we just did what I'm doing right now.
Yeah. we're
Okay,
back.
but since I knew I was going to do it again today, I didn't bother to save the notes. Because we're going to go more in depth and make things better.
The square or the boomerang brackets.
Uh-huh.
Does that mean anything? Is that
It was just letting you know it's a vector instead.
okay? Perfect.
So when you see the triangular brackets like that,
Yeah.
that's just indicating we're talking about a vector, not a point.
I've seen like if you draw an arrow, if you have 2 points and draw an arrow above them, doesn't that indicate a vector too, or something like that? I don't know.
Maybe that's a different notation for
This
it.
is better.
I don't
I-
understand where the root 13 came from.
Okay, so we got the root 13. Again, what we're doing here is this is we get this from doing the square root of minus 3 squared plus minus 2 squared, which would be root 9 plus 4, which is root 13. Okay, that's the magnitude. Okay. Basically, note here. Okay, if I redid this system up here, we drew the system fresh. Okay. This is what 1, 2, and 4, 4. Okay. We'll do the first vector. Like that there. Notice how I'm basically getting our values here by turning this thing into a right triangle. Okay. My x length here is 3, and my y length here is 2. Okay? And so, really, you can always think of vectors as basically being the hypotenuse of a right triangle. Okay? And we're just kind of codifying it down to be like this right here. Okay? Now, so this is how it works. Okay? Vectors in component forms. Some of the reasons why we do things in vectors as opposed to doing them with just regular points. One, this vector right here, 2, 3, this vector 3, 2, would be the same vector no matter where it is on the graph. Okay, so if I drew 2 other points, okay, let's put points up over here. We'll make this negative 5, negative 1, and then
Negative 3.
so we did negative 2, negative 1
Ah, yeah.
over here, okay? If I drew
Right, negative
the
1.
vector between that, okay? Well, the difference between negative 2 and negative 5 is 3.
Yeah.
Okay.
Don't you mean negative positive 2?
Oh, plus 1, yeah.
Oh no,
Plus.
plus 1.
Okay? And then the difference between 1 and negative 1 would be 2, okay?
Yeah.
And it's the same thing, okay? It's still 3, 2. So the vector, this would still be vector v, okay? Here. These are both vector v's. The only difference is where they are, okay? Because what the vector's encoding is not a position on the XY graph. Instead, it's encoding a direction and how long I went in that direction. Okay? So I went in the direction x3, y2, okay, for that length, okay, which would be root 13. Okay? Okay? There's another way, by the way, we're doing component form first. Component form's not that hard. Okay? And we're going to see how you do things in component form. Another way we could do it is in trigonometric form, okay? Which is instead, we go back to kind of the first slide. Notice how I wrote it in terms of the magnitude and angle. I could write it in trigonometric form that way, okay? I would say the vector is 13 cosine 33, root 13 cosine 33 and root 13 sine of 33. Because if I worked that out, guess what I would get? I would get 3, 2. Okay? So, that's just a different way of encoding a vector. We're going to see that later. Right now, let's just stick with the component forms. Okay? Any questions on how this works or how I make this up? Yes, George?
So, for V1 and V2, it's P1 minus Q1. Did you just write that as change in X?
Yeah. If you wanted to, go for it. Okay? The change in the x coordinates compared to the change in the y coordinates. Okay? It's just, the thing is, remember, it does matter which direction I'm looking at things in. Okay? So, am I going from 1, 2 to 4, 4, or am I going from 4, 4 to 1, 2? Because it will change the signs.
Yeah.
Okay? But otherwise, yeah. Okay, that's how that works there. All right? Any questions? Okay. Let's start talking about some of the properties of vectors, basic operations. Okay, so vector operations. Okay, we've got ourselves basically. There's several different operations we can do for vectors. What we're going to look at today are the two basic operations. Basically, vector addition and scalar multiplication. Okay, so the first one is vector addition. I would say dash subtraction. Okay. Okay. This is really super easy. If I add two vectors together, so let's say I have a vector given vectors v and u. I guess u and v, but whatever. Okay. Let's make it u and v, so that way, at least alphabetically speaking, we're following the correct. U becomes before v. So given vectors u and v, okay, u plus v would be equal to a new vector, okay, where it's the horizontal component of u plus the horizontal component of v, comma, vertical component of u plus vertical component of v. Okay? So you just add the numbers together, just making sure like component adds like component. Okay? By the way, if I made this u minus v, same deal, just make minuses. Okay? Just like so. Yeah? Yeah, you can use yours. Okay. Alright. So, take a look at an example of this. Okay? Let's say vector u was minus 3, 7, and vector v is 5, 12. Okay? U plus v is going to be minus 3 plus 5, which should be 2, and 7 and 12, which would be 19. Okay? You literally just add like component to like component. Okay? Not difficult, right? That's fairly straightforward. Okay? If I did u minus v, I get the same exact. I would do the same exact thing. So it would be minus 3 minus 5, so that would be minus 8, comma 7 minus 12 is minus 5. Okay, just like so. Right. what you're essentially doing, if we were to actually graph these things out, is we're essentially walking one vector, then walking the next vector in whatever direction it's indicating. Okay? So, an example graphically, okay, let's see, would I make, why don't I choose such big numbers here? Oh, well, fine. -3, no, I'm not going to use it. I'll just,
Scale it.
I will just draw two different vectors and just, okay, so we'll make this one here 1, 1. This is vector v, okay. This is vector u. So u plus v, okay, would be u plus v would literally be taking u and then adding v to it, like so, and getting right there. That would be u plus v. Okay? Any questions on how that worked? Yeah, it's fairly straightforward, right? Okay? U minus v, okay? Will be walking u, then walking the opposite direction. So we're going to call this now upside down v, but we'll make it minus v. Okay? And so we will walk along the line that way. Okay? Like that. And so you would get two different, that's what the vectors would look like there. Okay? We'll go into what's happening here with these lines here, because as you can see here, it kind of forms a little bit of a right angle there. Okay? We'll talk about that later, what's going on there specifically. Okay? But that's basically what we would end up getting there. Okay? Kind of connecting the dots. Okay? By the way, we did u then v. Notice how it's not going to really matter. Okay? Oops. Go back. Sorry. Wrong thing. If I did, come on, go down. Okay. Here's u, here's v. Okay. If I did v first, then u. Okay.
Still fit in there.
My line would be the same. Okay. Kind of graphically speaking. Okay. So you can kind of see there how necessarily with addition it's not going to really matter. With subtraction, it matters a little bit, but not too terribly, okay? I'm still going to get the same vector, it just might be pointing a different direction. It might be, instead of going down like this, it might be up like that, but still the line would be the same, okay? If I did things opposite. So, kind of keep that in mind when we look at these things, okay? Actually, here's what I'll make this. It's like a little easier. Okay, so that's how addition and subtraction works. Any questions? So if I asked you to add two vectors together, you should have zero problem doing that. Okay. If I asked you to add three vectors together, you should have zero problem. It's just one on top of another, just like that. Okay. You could literally just add a bunch of them together, and it's just basically. Kind of think of it almost like if you're adding a bunch of them together, it's like an old pirate map. Take, walk north, 20 paces, okay? When you or walk north until you reach like the forked tree, then turn right and walk, until you reach. That's essentially the type of thing you're going to get here. Okay. That's how addition and subtraction works. Okay, with vectors. The next vector operation. Next one we've got is what's called scalar multiplication. Okay, vectors scale nicely. Okay, in fact, one of the nice things about vectors and one of their uses is the fact because you can just scale them nicely. That they do some things like that. I talked yesterday to those of you who are here, about how computers, one form of graphics in computers is called vector graphics. Okay, and it's basically where the visual information is encoded as a vector instead of a series of pixels, XY pixels. The benefit being, if I zoom in, I don't lose any quality. Okay, or if I blow up the image, I won't lose quality. It's just the fact that kind of the difference is the vector graphics tend to look more cartoony and they kind of lose some of the details. Okay, but it all comes down to the fact that the scalar multiplication.
So it's a vector times a scalar.
Yeah, it's a vector times a constant, basically. Okay, so basically, how this would work is if I have, let's say, a given vector v equals v1, v2, and constant k, because constant starts with a k. Okay.
In Sweden, it does.
K times v would be equal to kv1, kv2. Okay.
Wow.
It's actually the equivalent, by the way, okay, of adding v to itself k times.
If it's
So like k was 3, it'd be v plus v plus v.
yeah.
Okay, just like regular multiplication, right? That's what regular multiplication means, okay? But that's essentially how it works, okay? So an example, okay, with numbers, and we'll do an example graphically as well, okay? Okay, let's say v was the vector 1, 4, and k was 3, then kv would be 3, 12, okay? 3 times 1, 3 times 4, okay? Just like that, okay? Graphically,
Just extends it out of mouth.
okay? There's vector v, okay? So, okay, so, one, two, 3. Okay? This guy right here, all of it would be 3v. Okay? Given that k was my 3. It's quite literally, again, just adding the same vector to itself 3 times. Okay? So what would happen if k was negative? What would it mean I'm doing? Okay? I'd be subtracting the vector from itself. Actually, what I'd be doing is flipping the direction and drawing it in the opposite direction. So if this was v, okay, if that's my v there, okay, we'll make this negative v, okay. Okay, so this would be negative 3v, okay? This would be negative v, negative v, negative v. Not to scale, but you get the idea, okay? It's just literally changing the thing and drawing it the opposite direction, okay, 3 times, all right? So yeah, scalars then will grow or shrink a vector, okay? So if I do a whole number, or not a whole number, if I do a number bigger than 1, okay, my vector is gonna get bigger, right? But if I did a vector, if I multiplied it by a number between 1 and 0, okay, it's going to shrink. Okay, so my vector is going to get smaller. All right. So if I did like, k was 1/2, I'd have 1/2 2, and my vector would be half the size. Okay. That's kind of one of the nice things about vectors is they scale nicely that way.
And then the number would turn it around. Right?
Yeah, negative would just flip the direction of the vector. Yep, flip its direction. Okay, and that allows you to basically draw your vector out kind of nicely. Okay, scale them out. Okay, that ends up again being one of the nice properties of vectors is that they do scale nicely. And so, by the way, because of this property right here, that's why vector graphics, when you enlarge the picture, you don't lose any quality. Okay. Because all the information is the same, it's just been stretched. Okay. While if you did that with a pixelated image, which is called a raster graphics, you would lose all, it would become big and pixelated. Yep.
Right.
So, 8-bit, okay, which refers to, the number of memory registers it has.
Yeah, so raster, does that mean anything?
It's just the name. I don't know specifically if
It's
raster
not-
means anything, but I do know raster graphics, that's like a bitmap image,
Yeah, yeah.
so pixels. Vector graphics, it's like SVG or PNG or whatever.
Apparently, the guy who invented vector graphics worked at an airline
Yep.
like thing, and
Yep.
he made a mountain, right? Or what was it? Like they created a plane that they haven't sold yet, and they had to have a mountain in the background. So he made a program that
That made
Could-
them vectors.
yeah, like a factor. I don't know.
I do know that one of the big uses of vectors you can use vectors for is like besides graphics, vectors are particularly good like telling things in physics. So
Yeah.
we'll do some problems like with an airplane where the airplane's flying in this direction, the wind's pushing it this direction, and so you're just adding two vectors together and the plane's actually going that way. So I'm flying my plane in this direction, the wind's pushing me, and I'm over here. That sort of thing, okay? Or the current, boat current kind of thing. Okay, same sort of deal. Anybody's ever driven a car with bad alignment? You're pointing the car one way, but the alignment's pushing it the other way, so you kind of veer off, okay? That's sort of basically, the addition of two vectors. Anyway, but that's how these things work. Any questions? Okay, I'm going to post these notes on Canvas along with homework for tonight, or I guess for Saturday, and I will see you then.